Okay, today's lesson is on bond and molecular polarity and dipoles. Now, the reason why we need to understand this is because a lot of solubility of things in other things is based on the polarity of the two materials that are trying to dissolve each other. So if you don't understand polarity, you won't have a good understanding of why some things dissolve and some things don't. Okay, so let's talk about bond polarity. When two nonmetal elements bond together, they share their electrons and we call that a covalent bond. However, in most cases, the sharing of electrons is uneven. In other words, one of the atoms gets more of the electron density than the other atom. In other words, the sharing of electrons is not equal. So somebody gets more of the electrons around them than the other atom. And so when we call that they're hogging these electrons. They're hogging electrons, and we base that off this term called electronegativity. Electronegativity, if you remember, is just the desire of an atom to acquire electrons during bonding. Okay, so now we're bonding, and so one of the atoms is going to want the electrons more so than the other atom. And when that happens, we get what we call a polar bond, a polar covalent bond to be more exact. And most covalent bonds have some degree of polarity. In other words, there is always a little bit of a shift of electron density in the bond towards one side of the bond versus the other. Okay, so if you remember back to the periodic table chapter, we talked about trends in the periodic table, and one of the trends we talked about was electronegativity. And we gave the definition there. The electronegativity is the desire of an atom to acquire electrons during bonding. Well, now we're in the bonding chapter, and we're going to revisit electronegativity. Now, electronegativity of an atom tells you how strong it wants to pull those electrons towards it when it bonds. So fluorine is the highest, oxygen would be next, and then chlorine. Notice that the inert gases don't have any electronegativity value. And why? Because they already have a full shell. They don't want to bond, so they're not bonding. So therefore, there's no desire to pull more electrons during bonding. So these elements here are all our nonmetals, and they're going to be the ones that we're concerned with when we do a covalent bond. So the moral of the story, I guess, is whoever has the highest electronegativity in a bond will have the electron shift more towards them in that bond. Okay, now that we know what a polar bond is, how do we determine whether or not a bond is polar or not, and to what degree? So there are only two cases where you have a nonpolar bond. Case one, when both atoms are exactly the same. So when they're both exactly the same, nitrogen bonded to nitrogen, carbon bonded to carbon, oxygen to oxygen, fluorine to fluorine, etc., etc. The bond by definition is nonpolar. There is no electron shift because both atoms are pulling the electrons equally. We're going to consider for this class carbon-hydrogen as a nonpolar bond, mostly because the properties of carbon-hydrogen materials, gasoline, wax, things like that, are extremely nonpolar. They don't dissolve in a lot of the polar solvents, very little. So we're going to consider them to be nonpolar, right? Everything else, if it doesn't fit these two classifications, one of these two classifications is going to be polar. Doesn't matter what it is, right? Carbon, sulfur, hydrogen, sulfur, oxygen, sulfur, whatever, right? Now, if you were to compare two bonds, you wanted to say, well, which one of these two bonds is more polar? That's when you need to look at the electronegativity differences between the two atoms making up the bond. So I've done that here. We want to compare these two bonds. Which one is more polar? That's the question, right? So I look at the electronegativity difference between this one, and then compare it to this one and this one. So here's my oxygen. I looked that up. That's 3.5. I looked at the electronegativity difference of electronegativity of hydrogen, and that's 2.1. I do the difference, and I get 1.4. I do the same thing for the fluorine-hydrogen bond. All right, 4 minus 2.1 is 2.9. So the HF bond is more polar compared to the OH bond, right? It's all relative, right? Now, let's say you don't have two, you're not comparing two different bonds. You just want to know whether or not relatively if a bond is very polar, polar, or weakly polar. Well, now you can just look at a chart, right? So you get the electronegativity difference, and you're going to say, for our class, if it's greater than 0.8 or equal to 0.8, the electronegativity difference, we're going to say it's very polar. Some people have said that this should be greater or equal to 1. It doesn't matter really, as long as it's really high, a number. Anywhere from 0.4 to 0.8 is going to be considered polar. Less than or equal to 0.4, very weak polar, right? If you did this, you get En equals 0, that only happens when you get these, right? So when you get to this thing, if it's polar, that's when you would use this chart. Nonpolar, the electronegativity difference by definition is 0. Okay, I went through that pretty quickly, but basically what you're looking at here is this is the first rule you apply. Once you have a polar system, then you can look at comparing two different polar bonds using this technique. If you only have a relative value, you want to say, well, is the bond polar or very polar? That's when you would use this chart, right? Okay, like polar bonds, polar molecules have an electron density shift from one side of the molecule to the other. In order to get that, you must have a polar bond. If you do not have a polar bond in your molecule, there is no way you can get a polar molecule. You need to have at least one polar bond. However, you can have a molecule that has polar bonds but not be polar. Well, that sounds counterintuitive. You just told me that I need to have at least one polar bond, but if I have polar bonds, wouldn't that make the molecule more polar? And that's not necessarily the case. You need to look at the spatial arrangement of the bonds relative to each other to see if you have a electron density shift. And that's where the Lewis structures come into play, and we'll show you that in a minute. Okay, so there are a couple of rules that we're going to use to determine whether or not a molecule is polar or not. First rule is, if you're looking at a binary compound, a binary molecule, which means it has only two atoms making it up, such as O2, N2, HCl, HBr, CO. If both atoms are exactly the same, then you have, by definition, a nonpolar molecule, because nobody wins the war in electron shift pull. If the atoms are different, then it's polar. It's that black and white. Two of the same, nonpolar. Different, polar. Now, if you have more than two atoms, you need to look at the Lewis structure for that particular molecule. So you might have to draw it. Now, here's the key on that one. You have to look at everything coming off the center atom. If everything is the same, then it's nonpolar. If anything is different, then it's polar. That's it. As long as one thing is different coming off the central atom, then it's polar. If everything is the same, it's nonpolar. So let's see what that means in the next slide. I'm going to tell you that this slide right now has a mix of polar and nonpolar molecules. These are tertiary molecules. In other words, they have more than two atoms. Binary means two, tertiary means more than two, right? So our first atom, our first molecule is water. And what I'm going to do is I'm going to go through each one of the molecules real quick and just circle the central atom, because that's what we're going to be keying off of. So there's my central atom in my water molecule. Here's my ammonia molecule, that's the central atom. My CO2, that's my central atom. And my carbon tetrachloride, that's my central atom. Okay, now we're going to go back and we're going to look at all of the things that are coming off of the central atom or attached to the central atom. So here's my water. There's 1, there's 2. These are attached. The lone pairs count, as I said before. They count. So there are 4 things attached to the central atom. Now, are all the things exactly the same? In other words, is hydrogen the same as a lone pair? And it's not. So by definition, this is polar, because not everything is the same. Not same, polar. Same, polar. So let's go down here to my ammonia. So here's my first thing attached, second thing attached to the center atom, third, and my lone pair. Again, is everything exactly the same? The answer is no. The lone pair is different than the hydrogen. So that is also polar. Okay, now we're going to go over to the other side of the page. We're going to circle everything that's attached. There's my 1 oxygen, and there's my 2nd oxygen. Now, is everything exactly the same? So we're going to look at this, and we're going to say, okay, so I'm going to look at this, and I say, well, I got an oxygen here with 2 lone pair, and then that. I got an oxygen here, 2 lone pair. It looks the same to me. So everything is the same. So this is nonpolar. Remember, nonpolar means everything is the same. And the last one is, let's look at the carbon tetrachloride. There's 1, there's 2, there's 3, there's 4. Is everything the same? Well, let's quickly look. Yep, it looks like it. Chlorine, 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 chlorine. Everything looks the same to me. So again, this is nonpolar. Now, here's an example of when you have polar bonds, but not polar molecules. All right, so let's look at this real quick. Let's circle the polar bond here. Here's my polar bond right there. Okay? And let's circle the other polar bond right there. Okay? So now we're going to look at both polar. Are both bonds polar? Yes. Are they the same? Yes. So they're going to be pulling in equal and opposite directions. So it's a tug of war, and nobody wins the tug of war. There's no shift. This oxygen is not stronger than this oxygen, so it doesn't win the battle, and this doesn't win the battles. So if there's nobody winning the battle for pull of electrons, then there's no shift. No shift means that then it's nonpolar. And you could do the same thing down here. We know that by definition, the carbon-chlorine bond is polar, but you have 4 of them, and they're all pulling equally, in their respective directions. Therefore, the shift doesn't happen. So, 2 examples of when you can have polar bonds, but a nonpolar molecule. So polar molecules have dipoles, and dipoles are just separations of charges within the molecule. The molecule itself is still neutral, electrically neutral. The electrons are all still on the molecule, just move to one side or not. That's all. So again, the dipole results from an imbalance of electron density. Only polar molecules have dipoles. If you say where's the dipole in a nonpolar molecule, there isn't any, because there's no imbalance of electron density. The side of the dipole that has the more electron density, is the more negative side of the molecule compared to the other side with the less electron density. That does not mean that the side of the molecule is negative, like an ion. It just means that it has more negative character than the other side. And that is a big deal when you talk about intermolecular bonding. To convey that a molecule is a dipole, there are 2 symbols that are used generally. And these are the small delta and this arrow head with a cross. I call it the cross arrow. Now, I like using this one because it tells me a lot of information. It tells me which side of the molecule is more positive. It tells me which direction the shift is, and it just points. So that's a visual indicator for me. I like that. This one, you have to add a charge to it, either a plus or minus, to tell you which side the molecule is more positive or which side is more negative. It's not as visually easy to understand as this one, I care. But a lot of scientists don't use this. They use this. So I'm teaching you both just in case. Okay, so these are the same molecules we just did, and we're going to X out the ones that are nonpolar because they're not going to have a dipole. So there is no dipole here because they're nonpolar. Now, I'm going to do both ways for the other one. So again, the shift is always towards the more electronegative element. So in this case, where would be the shift? The shift, if you were to do the arrow, plus arrow thing, would be in this direction. Right? Because there's two of them, and that's the way of the shift. Now, if you were to use the delta things, it would be, you would write it like this. This would be more positive, same with here, and then this would be negative. Okay? And you don't use both. You don't need to use both. You can either use the arrow or the small deltas. But I like the arrow because it's more visual for me. But you can use either both. One or the other. Now, the other one, let's look at the other one that we said was bound. So if we do the arrow again, everything is going to point towards the nitrogen. Right? And we got that. And so if we were to do the things again, we would say that this would be, oops, that's orange. We don't want that. We want the purple one. That would be the plus. This would be more plus. This would be more plus, and then this one would be more minus. And there you go. So again, you don't use both at the same time. It's either one or the other, but I would just show you how they could be graphically represented by either or of the symbols that we could use. Remember, non-polar molecules do not have a dipole. They do not need to be labeled as dipoled.